Welcome again to the NPTEL course on storage systems. So, the last two classes we have been looking at the Google file system, and basically in the first part of this we looked at the GFS high level design, and in the second part of it we looked at the consistency management, and basically we went over some aspects of this model. Basically that you might have what is called either a defined situation with respect to a file, or it could be consistent but not defined, right, undefined. So, basically because of concurrent write operations, different chunks could be written in different, even though they are getting written to all the replicas in the same way, the actual chunks may be written in different orders. Okay. So, that is the reason why it can be consistent but not defined. Okay. Of course, if there is a failure, you can have inconsistency. Okay. And similarly with record appends also we have a similar situation. Once you succeed, it is defined, but it might be that there are some earlier parts, okay, at lower offsets, which are some stuff that was put in, but could not be carried forward because some chunks chunk servers failed, or they could not complete that part of the write. Okay. So, that is basically what this is. Okay. So, so we went through some of this last time, and we also looked at a bit about how the application design has to change a bit. Okay. And the good thing about this particular design is that if you use appends, you do not really need a heavy duty distributed lock manager. So, basically you try to avoid the costly consistency and concurrency issues by a slightly different, simpler method. Okay. So, again we looked at this write control and the data flow, and basically what we mentioned was to ensure that you can exploit the bandwidth in the system as soon as the client figures out where the chunk locations are, where the primary is and where chunk locations are, it can start pushing it immediately. And then once all the locations, primaries and secondaries, report that they got the data, then the client actually does the actual act of committing the writes, because all the data will be actually sitting in some temporary area, and then once the write starts, then the primary will decide on a particular order, and then all the mutations that are going on at the same time, if all the writes are taking place, and then each of these secondaries will actually write those things in the same order. Okay. So, this design is slightly different from the ones we saw before with respect to group communication systems, where the bandwidth issue is not taken that seriously, okay, because this is a large scale file system, massive scale system. This bandwidth issue is an important one. So, basically there is I want to continue from here. As I mentioned earlier, there could be for each chunk there could be a current leaseholder, and you want to check, if you want to do a write operation, you want to check who is the party who has got the lease. Okay. And once you get the leaseholder, that is the primary, and then other people who other replica locations, they will have the chunk replicas. Okay. And that is how the client gets going. Now, there is some aspect relating to the lease management also. Usually you want to minimize management overhead at the master, and the way they do it is by having the initial lease only for 60 seconds. So, if there are requests that come in within the 60 seconds, you do not have to go to the master again. 60 seconds was considered to be a reasonably good amount of time. Okay. Again, you will see that most file systems typically have leases around same amount of time, 30 seconds or multiples of 10 seconds. This turns out to be slightly longer. 60 seconds looks a bit slightly longer, but I think this makes sense because these operations also take longer because we're dealing with large 64 megabyte chunks. Okay. And the primary can request and typically receive extensions indefinitely. As long as it's actively using it, it can keep on doing it. And there's not much extra overhead because anyway you are going to use heartbeats for checking the health of the chunk servers, and then basically any lease request can be sent as part of the heartbeat itself. To basically you can keep telling that I'm alive, at the same time saying that in case you have to get any leases, you can put that in the same message and send it out. Okay. And basically you can the master also has some control over things. It can revoke a lease before expiry. For example, if there is a file that is getting renamed, you want to prevent mutations on that file while this concurrent operation is going on. You want to avoid that concurrent operation, and therefore you can essentially take back the lease. Once the lease is taken back, then there is no way anybody can modify that particular file. Okay. Again, one advantage of lease management is that with the leases is that even if master loses communication with primary, it is safe to grant a new lease to another replica after old lease expires. That's basically the standard reason why you use leases. Basically, it is communication through time rather than communication through messages. Okay. So, but this requires that once you have communication through time, that means you need to have time synchronization as a critical part of it. So, it has to be reasonable. Okay. But it turns out that in this particular system, they do cache metadata for some periods of time. So, the kind of inconsistencies that are there anyway are going to be here with respect to metadata. There is some problem. Again, this is similar to what happens in NFS. Okay. There are similar issues here also. So, even if the time synchronization is not very, very accurate, it is still manageable because the semantics anyway assumes that there is a possibility of looking at stale metadata for some period of time. Okay. Just like the writes, you can also do the record appends. It is very similar. Only thing is that we have to worry about the last chunk of the file. In the case of a write, it can be spanning multiple chunks and you have to split it, and various aspects of that have to be done. There could be also let us say read, modify, write cycles, etc. that is there as part of the write. Okay. Whereas in the record append, basically you have to look at only the last chunk. Okay. So, the client sends request to primary. Again, just like previously, primary checks if append exceeds the max size. If so, pad chunk size, pad the chunk to max size, and then it tells the secondaries to do the same thing. It says you also, I am going to pad it, you also pad it, because and then again it goes back to the client and says, I have not done anything for you so far, but please retry it, we will proceed after that. Okay. Because all it has done is to pad the chunks. Okay. Whereas in the case of, for the common case, usually whatever is being written usually fits into the maximum size. So, it tells the secondaries to write data at its own offset and report success to client. Okay. This is a simpler case. Okay. Now, we have to wonder about what happens if there is a failure. The record append fails at end replica, client retries operation. Okay. So, that is how you may find that the replicas can diverge in the content of what they have. Okay. Replicas of same chunk may contain different data, possibly include duplicates of same record in whole or in part. Okay. Basically, some because of this issue, GFS does not guarantee that all replicas are byte-wise identical. Okay. So basically what happens is that you retry, some guys might have succeeded, some guys might not have succeeded. Those guys who have succeeded have written something, and those guys who have not succeeded have not written it completely or partially they have written it. So they will be diverging. Again, when we retry the whole operation, what will happen is that everybody gets a new offset, but whatever junk that they have put in previously, whatever has failed, that still remains there. Okay. That's the reason why GFS does not guarantee all replicas are byte-wise identical. It also can happen because of some chunk server is down, or so because it's down, it's not able to take this particular let's say data, and so it can become stale. So you have to have another protocol by which these stale replicas are detected. Okay. So what GFS on the hand guarantees is that the data written at least once as an atomic unit. You are trying to append something, it is giving you at least one semantics. That means it has possibly written multiple times, but all the previous times are failures somehow. And then, but finally if it succeeds, there will be at least once it has written the whole thing properly at all the replicas. The append has succeeded at all the replicas. Okay. So for opt to report success, data must have been written at the same offset in all replicas of some chunk. Okay. All replicas at least as long as the end of record, and any future record will be assigned a higher offset or a different chunk, even if a different replica later becomes primary. Okay. So even if when the primaries change and whatnot, we can guarantee that any future record will be assigned a higher offset. Okay. Or it will be in a different chunk altogether. So regions in which successful record append ops have written the data defined, they become consistent, whereas intervening regions inconsistent. So wherever the successful record appends have taken place, they will be first of all consistent because all of them are writing in the same order. Okay. And that order is fixed, and it is made sure that all the data is available to all the clients, all the primary secondaries. Only when everybody has got the data, then they start writing it, and they all write at the same offset. Okay. That's why it will be, that particular region will be both defined and consistent. It is consistent because they are all writing the same things. It is defined because all of them also would have completed their thing, otherwise it is not reported as success. Whereas before this particular successful append, there could have been some problems. That is why the intervening regions are inconsistent. Okay. Some have written it, some have not written it. Once they have old information, some have new information. So another thing that GFS does is they provide something called snapshots, and basically this is needed for standard reasons why snapshots are useful. You want to make a copy of a file or a directory, and it could be for backup, it could be for you want to make some modifications, and it's not clear that the complex modifications may go through successfully. So you want to make a snapshot of it and do it on a branch, and later decide what to do with the update, whether if it succeeds. Okay. So because you are going to make a copy of file or directory, especially directory, you have to make sure that you have to minimize interruptions of ongoing mutations. Okay. This snapshot should not basically stop the ongoing mutations, ongoing changes. Okay. So it basically uses a standard copy on write kind of mechanism. When a master receives a snapshot request, it revokes any outstanding leases on chunks in files to be snapshot. Basically, if you are going to snapshot, you want to make sure that no client is actually writing to it. Therefore, you basically try to get back all the leases so that it is clear for you to start doing a snapshot. So if there is any later write to these chunks, first find the leaseholder for master, and then master can now create a new copy of chunk. Okay. So, after any cow has taken place, if there is any later write to these chunks, you first find the leaseholder from master, get a lease, because the client has to find the leaseholder from master. The master will actually allocate a new lease for it, and then the master can now create a new copy of chunk. Okay. Now, the master also logs the operations to disk. First, it applies this log record to its in-memory state by duplicating metadata of source file or directory. Basically, in a snapshot, you have a source and the destination. So, basically, you duplicate the metadata of the source file or the directory first, and then actually you log all these things to disk. Okay. Just like in any standard snapshot, newly created snapshot files point to same chunks as source files. Once the update happens, then there will be that connection which is broken. Okay. So, if a new client wants to write to a chunk C after snapshot, sends the master to find current leaseholder, right. Basically, a snapshot has been done, and there could be other things going on, and then somebody wants to do a client write to chunk. So, sends request to master to find current leaseholder. Somebody else might be having the current lease. Then the master notices the reference count of the chunk being greater than 1. So, if the master notices that the reference count is greater than 1, then it knows that it is a snapshot, it is connected with snapshots. Okay. So, instead of replying back to the client immediately, it picks a new chunk handle C prime, then asks each chunk server with current replica of C to create a new chunk called C prime, because now the write is going to go to this C prime. Okay. And they have some interesting optimizations. They make sure that the data is copied locally, not over network. In their systems, when it was designed, disks were certainly far more faster than Ethernet. That is why it is done locally, not over the network. Okay. So, now once this has been done, the request handling again is the same as master grants one replica a lease on C prime, and now C prime is starting to write on C prime. Okay. The only difference in the beginning, when the client wrote, there was this chunk C which had a reference count of greater than 1. That means it was also part of that same chunk, was part of two views, one of the old file system and the new of the snapshotted file system. And because the reference count is greater than 1, you had to allocate a new chunk C prime, and now the client actually can write to C prime directly. Now that particular chunk has been decoupled from the previous file system. Now, just let us just look at all the what all the master operations. I think as we discussed so far, it executes all namespace operations. For example, if it's a question of adding a file, deleting a directory, etc. The master also manages all the chunk replicas, makes placement decisions, because it is the only single entity which knows all about the whole system. It can make all this fairly quickly, and everything is done using information in memory, so it is quite fast also. It also creates new chunks and also new replicas as necessary. So, if the chunks, sometimes if there is a replication factor of some amount, and some of the chunk servers may go down, so it may turn out that the number of replicas may not be as much as necessary. So, it does some system-wide activities to make sure that the replication level again goes up. Those kind of things also it does. It has to balance load across all chunk servers and also reclaim unused storage. Now, one thing interesting about this particular file system we will discuss again later is that the deletes are not done eagerly. That means, as soon as you tell a delete, you do not immediately reclaim the space. It is done lazily. So, the idea being here is that you have a scan of the whole system at regular intervals, or there are other for housekeeping operations. During that time, you notice those deleted files and their corresponding chunks, and then you reclaim. You essentially do some kind of garbage collection. So, they have a garbage collection phase which does that. Okay. So, that we will discuss this part of it brief, later sometime. Okay. So, again it turns out there are some operations take a long time, and just like any standard file system, a concurrent file system, you take basically locks over regions of the file system. Okay. If you want to get concurrent operations on multiple parts of the file system, there has to be locks taken on different portions of the file system. That is what this also does. Okay. Example, snapshot takes a long time, and it has to revoke all the leases. It will take some time. So, if you are taking, if you are not taking for concurrency, you need to ensure that other party is not connected with the snapshot operation. They should be able to proceed, but you should be able to stop those guys who are encroaching on the part which the snapshot is doing. So, you need to take a lock corresponding to that. Okay. So, you want to allow multiple operations to be active at the same time, and therefore, you need to use multiple locks to over multiple regions to ensure proper serialization. So, let us just look at some aspects relating to this directory operations. One thing about this particular file system, which is somewhat different from a regular file system, like for example, ext3 file system in Linux, GFS does not have a per directory data structure that lists all the names in that file in the directory. So, all it has is a lookup table mapping full path names to metadata. Okay. So, because of that, it turns out you have a per directory data structure. Okay. So, you can't go to a directory and say list all the files there. Okay. So, it uses prefix compression to store the names. That is why it is efficient limit. Basically, the idea here is this, that suppose you have a file d1, d2, dn, finally the leaf node. Okay. This whole thing is thought of as a single name. In a regular file system, you first go to d1, locate the directory structure corresponding to d1, and then search for d2 in it. If d2 is there, then again you search for something, etc. Right. Here, the whole thing is looked up in one shot. Okay. So, that is that lookup table. Full path names are mapped to metadata directly. That means, you give it this, it just goes and does some hashing or something, immediately finds a corresponding entry and it gets inode, equivalent of inode. Okay. And because of this, it does not have any hard or symbolic links. It turns out, when you are doing this kind of stuff, you can't have hard or symbolic links, because if you want to have hard links, then you need to have the notion of some place where each of those new names for these hard links are present in a particular directory. You need to have those kind of notions. This one is not there because it does not have a per directory data structure. Okay. So, each node in namespace tree, whether it is absolute file name or directory name, has also a read write lock, because you want to allow a lot of concurrency, and normally when you have a tree structured file system like this, d1 / etc., some operations down below can actually cause some congestion at the top. We will look at it soon why that is the case. So, it has both a read and write lock. Read lock is used so that nobody can change it, whereas write lock is there that you are the only person who can change it. Okay, both things are taken. Okay. For example, if you are doing an operation on /d1, d2, dn, df, leaf, then you would take for example all the read locks up till this point, and depending on the operation, I want to take a write lock, okay, on the full path name, okay. So you take read locks only on each of the directory names, okay. So this allows concurrent mutations in the same directory, okay. So if you are doing, for example, multiple file creations in the same directory, you can acquire a read lock on the directory name and a write lock on each of the file names, and that's perfectly fine, because basically all you are saying is you are not going to change the path name, it is intact as it is, but you are going to change the file. That is why you are going to take a write lock on that. Notice that in the case of a regular file system, you need to take each party has to take a lock on DN, because they are going to add something to the directory. You modify something in the file, you are adding a create, for example, you are doing a create, for example, you are going to add something to a directory. So if you want to add to the directory, that has to be exclusively written, the directory itself has to be written. That means that if you want to do multiple file creations, they will have to take a write lock on the directory entry also. Whereas in this case, they are just basically taking a read lock on the directory name, okay, and a write lock on the file name. So this allows for a slightly amount of concurrency, okay. But then the thing is that they have to do you need to have a map which maps full path names to method, okay. Unless you use tricks like preface compression, it is going to be expensive, okay. Let us look at one example of how they achieve this one. I will also relate this to a different problem and some other file systems, okay. Suppose I have the following situation. I am going to do some snapshotting, and then while this is being snapshot, for example, there is some /home user is being snapshotted to /save user. The intent of this being, of course, that somebody is saving or backing up the current state of your user directory exactly as it exists, right. You just want to back up. That is being backed up to save user, okay. Now while this snapshotting is being done, I want to ensure that the user is not able to create a file. Let us say I want to do that, okay. So the way this is done here is the following, okay. So let us look at the directories /home, user and foo, okay. So if you want to create a snapshot, you are supposed to take a read lock on /home and a write lock on the user, whereas when you are doing a create, if you want to create a foo file, for example, what is going to happen is that you are going to have a read lock on this, a read lock on this, because the idea is that nobody should be changing the path name while I am creating a foo. That is why this is both a read and then this will be write, okay. So suppose I look at the snapshot itself. In snapshot, /save should be R, because it is read only, again the path name should not be changing, that is why I am taking a read only lock, whereas I am modifying the user because I am copying whatever is here into this one, so that has to be write. You notice that for create you are taking a read, for snapshot you have taken already a write. Because you have taken a snapshot and write, nobody can get a read lock, okay. Again this, if you think about it, the idea is that when you are doing a snapshot, what did we say it was? You are going to okay, let us see, where was this? So if you are doing an operation, right, you are going to take a read locks on all these directory names, okay, and then you take a read or write lock on the full path name, right. So because of this, when you think about it, you are going to create on user a read lock is required for the create, whereas snapshot to ensure that nobody else can modify it at the time it is being created, we take a write lock, and the two things are, let us say, not compatible, so only one of them can proceed. So if you have already started the snapshot, nobody else can create a file. Okay. Now, if you think about it, this solution essentially helps you to avoid some complicated contention problems. I will just illustrate this with taking an example from a regular file system, okay, which does not have this notion of a full path name to metadata mapping and does not have per directory data structures. Suppose we have a system called hierarchical storage management. Okay. What is this? These are some are basically you can have a system that has got some files which are stored in tape. You have some disk files and also on tape, and then once in a while when some files have become very old, you want to send it out to tape, and then when you require it, it is picked up from the tape and brought back. Okay. So suppose some guy wants a migrates somebody, there is already a file in the tape now, you want to migrate it inside to the disk. So the party who is doing is what we call the perpetrator. This is the guy who is going to bring it in to the disk. Okay. And to do that, you basically have to log that particular things to make sure there is no other concurrent operation on that object. Okay. It is not yet made to the disk, but you want to make sure that nobody else also attempts one more activity of that kind or whatever, right. So that is why you are taking a lock on it. Now, while this is going on, somebody innocently tries to look it up, let us say. Okay. So in conventional file systems, when you are looking up a file, you have to log the directory where it is existing, because otherwise somebody could concurrently delete it, for example, and then so therefore you cannot know, you don't know what answer to give them. Okay. So basically when you are looking up, you try to log the directory. So if you log the parent directory while the lookup is going on. Okay. Now the problem for us is that the file is getting migrated, it is coming from tape. It takes multiple seconds, let us say 5 seconds, whatever, or even 50 seconds. That means that the parent of directory is locked up for that amount of time. Okay. Because this guy, the guy who is trying to look it up cannot succeed till the migration has completed. So this guy has got a lock on the directory, and so it keeps hanging there. Okay. If suppose somebody else tries to look up the parent of directory, okay, then that guy also will hang, and if you get just a few of the by sheer bad luck, if all of them tries to go up to slash 4 or 5 of them, right, if there is the depth is only 3 4, let us say, and by bad luck the migration is going on, and each of the guys, some there are other 3 or 4 other processes which are looking up those components in the directory path, the whole system essentially can hang. Okay, the whole system, because slash is stuck and everybody is stuck now. Okay. So those kind of things can happen precisely because you are trying to take a lock on the directory per se, because the directory has the notion of having those files, and they have to be, if you are updating anything, you have to take a lock on the directory. Whereas in this kind of systems, you are taking a lock on the path name, not on some structure called directory. Okay. And that is why it is slightly easier, it will be less problematic. But the problem with this solution is that you don't have hard or symbolic links. Okay. Basically because you can't have hard links, because hard link by definition has 2 different names for the same thing. That means that you have to create some way of hashing 2 different names to the same object, which is not possible. Okay. So because you can create arbitrary hard links, so there is no arbitrary hash function which can map 2 different names to the same thing with arbitrary path names given. Okay. That's why you cannot have hard links. So that means that the kind of saving etc., some kind of savings etc. that you can do with regular file system not possible. But the advantage of that is that your directory now can, let's say you don't need a directory per se, only path names, you actually are locking on a path name rather than on a directory, actual directory structure. So basically this, so because you are taking, you are going to have some lock objects, read write, and there is a large namespace with many nodes, and you do not want to create read write objects for each one of them. Okay. So these read write lock objects are allocated lazily on demand. Okay. And if they are not in use, they are deleted. Okay. Again, locks are always taken in a consistent total order to prevent deadlock. This is basically the standard attempt at two-phase locking kind of models. Okay. Ordered first by level in the namespace tree, next within the same level. Basically, if there are multiple people walking up and down the directory namespace, you have to always have the notion that when you lock it, you take it in the same order. You start from the top, go to the next one, etc., rather than some guys going up and some guys going down. If you do that, you get into deadlock situations. Okay, that also is there. Now, coming to a few other aspects of the system, you also need to handle how to do replica placement. Each of this has been, a lot of details are there. I am just highlighting some aspects of what they have done. Okay. Now, there are hundreds of chunk servers and clients spread across many machine racks crossing many network switches. So, how you place your replicas will actually determine how well you perform. Okay. Not only that, there are issues like you have bandwidth going into the rack or out of the rack, maybe much less than the aggregate bandwidth of all machines in the rack. For example, if you are having something like 40 machines on a single rack or like 20 machines, then it turns out that the bandwidth between them can be much higher than if you are again taking the, let us say, some network connection out of the rack. That will be basically the maximum possible in the technology at that time. For example, when these people did it, it was gigabit Ethernet. So out of the rack will probably be 1 gigabit, whereas if you have some 20 or 30 machines, each of them with 100 megabit per second, let us say, that is certainly bigger than the 1 gigabit connection. Okay. So because of this, your replica placement has to be managed in such a way that you maximize data availability and reliability and also network bandwidth utilization. And the way they do it is by making sure that the chunk replicas are spread across the racks. There are some positive things about this and some negative things about this. The positive thing about spreading chunk replicas across racks is that the data survives even if an entire rack damaged or offline. In real big systems, typically there are many correlated failures. For example, one power supply, in spite of redundancy and whatnot, the power supply can be problematic and the whole rack might be powered down. Okay. So in that case, if you don't spread your chunk replicas across racks, you might lose the availability is compromised seriously. That's why it has to be done across. Another nice thing about doing this is that if you want to do a read traffic if you want to do a read of a chunk, you are essentially now have the aggregate bandwidth of multiple racks. Okay. You are not actually fighting to get 3 chunk reads going to the same rack and all of them flowing out of the same connection from the rack to the client. Okay. You basically now have 3 different connections from 3 different racks which are coming to the client. So basically, if it is read traffic for a chunk, it is actually a good solution. Whereas for write traffic, it's a problem, because if I want to write to multiple racks, actually I have to send multiple copies to each of the racks. Okay, I can't forward it from one machine inside the rack to another machine in the same rack. I can't do that. So there is a problem here with respect to write traffic, but again, they have decided this is a proper trade-off to make, because they are usually more into heavy reads rather than heavy writes. Okay. Basically, this again is the design optimization. Basically, depending on the way you are using the file system, you have to choose, and they have decided that it's better for me to be able to exploit the aggregate bandwidth of multiple racks for reads than suffer. It's okay to suffer with respect to write traffic, having to make 3 independent writes to 3 different racks. Okay. That will essentially reduce the bandwidth of other things, because all the 3 racks are getting used up with respect to write. So there are quite a few other operations that have to be done. When you're doing chunk creation, you have to think about where to place the chunk, for example, right? During chunk creation, this is for re-replication, rebalancing. Suppose, for example, a master creates a chunk. You have to choose locations for initial empty replicas, because in the beginning, before there's nothing been returned to the chunk. Somebody, let's say, is doing a append. Okay. So you have to figure out where to choose it. So they have various heuristics, fairly straightforward. Place new replicas and chunk service below average disk utilization. That's first number. That's one kind of heuristic. At the same time, they want to ensure that limit number of recent creations on each chunk server. Okay. Basically, the issue is that the creation may be cheap, but if you create too many things, just behind it all kinds of write traffic also will come. Okay. Because usually what they have in their kind of system, if append once, read many, basically the append once, read many workload, typical pattern. Okay. And once it has been completely written, it becomes read heavy. Okay. So basically the thing is, the reason why you are creating a chunk is because somebody wants to write. Okay. Once you have finished writing it, it now starts becoming read only, heavy traffic can start after that. So that means that it becomes likely that if you create too many of them on the same chunk server, then there will be too much write traffic going to that particular chunk server, and that particular thing might be overloaded. So, and you also, just like before we mentioned, you spread replicas of the chunk across racks also. Okay. Now this is one case, master creates a chunk. Okay. Then there are similar issues like master re-replicates a chunk. For example, it turns out that one chunk server dies, so you wanted 3 copies, now there are only 2 copies. So you want to re-replicate, okay, so that number of available replicas is back to normal. Okay. Now again, there are a lot of interesting possibilities. This particular system has certain policies for doing this. For example, it turns out that there are some chunks which are blocking client progress because they are taking too long, they are overloaded. Okay. If you notice those kind of situations, you boost the priority of that chunk, okay, so that you can have a new replica for that one. That is, okay. If you are also lost too many replicas, for example, you wanted to have 4 copies, now you may have lost already 2, then that means you are lost more than you expected. Typically at the most you want to be at the most 1 away, for example 3 or something like that. If you already lost 2, then that becomes very high priority. Okay. Other thing that we want to do is to make sure that the bandwidth is handled properly, limit number of active replications in cluster on each chunk server. If you have too many active replications, then that also will have a interfere with actual work that is being done, because these things are all basically management operations. They are just so that your comfort level is good, that okay, I wanted 3 copies, there are 3 copies. They are actually not doing anything with respect to the actual client requests. So this management operations can essentially suck away all the bandwidth. So the idea is to also try to see if we can limit the number of active replications. Other thing the chunk server does is it limits replication bandwidth by throttling read requests to source chunk server. So even the chunk server also can essentially play a role if it can throttle read requests in case basically the number of replications required is too high, it tries to throttle it also. Okay. There's also the system also, the master also rebalances replicas again with respect to load balancing. Okay. Again here most of the ideas are similar to what we already discussed. Okay. Basically you want to ensure that there is not too much bandwidth taken up, okay, while you are doing the rebalancing, okay, etc. Those kind of things. I already mentioned this a bit, but basically this particular file system is slightly unusual because files are deleted lazily and garbage collected on regular file system scans. So all you do is you write down the delete time and then leave it there. You don't really delete the file. Okay. And interestingly also in this system they have, even if something is deleted till actual garbage collection, the file that is deleted is available under hidden name. Again this is sort of similar to even NFS, for example, when we have the open but delete situation, right, the server will actually rename that file, okay, with a inaccessible name, right, which the clients on that particular client which deleted it can actually access. Okay. Something similar is going on here also. Okay. And I am told that you can even rename this hidden name to what you need in case you find that there is a reason why you want to get back the file. Okay. Those kind of things are possible. Okay. One thing there's an interesting thing about this particular design is that they found eager deletion to be problematic. Basically because when you want to delete something, the master has to send delete messages and they may be lost. Okay. And it may be that the machines also die. Okay. That means that if you think that you are deleted, somebody has to keep track of, I have told them to do it, but they might not have done it. Right. The master has to keep on thinking about it all the time if you do eager deletion, which is a bit of a big overhead. So the idea is that why go into that kind of situation? You just do it lazily and do it when you have to anyway scan the file system for other reasons. It could be for many reasons. For example, it could be that you are scanning it because you want to see if any disk block has gone bad. Normally what happens is that disks suffer from something called latent errors. So to catch those things you scan the disk every so often. Okay. So there are various scans of that kind in the system. So why not piggyback on those kind of scans and detect those things that have to be deleted, because you marked it as deleted. At that time when it is deleted, you just at the time when you are doing the scan you release it. Of course this is a problem, because this can be a problem because if you are very close to the end of your storage availability, space availability, this kind of systems also will create some problems, because that you have to actually be not lazy about it, you have to be active about it, eagerly have to do certain things at that time. Okay. Other reason why eager deletion is problematic is because write errors create garbage chunks unknown to master. Okay. Basically the chunks are kept by the chunk servers and certain parts of the disk can suddenly go bad. Again I mentioned latent sector errors. Okay. And these are not known to the master. So you need to have some, if really you want to do a eager deletion, proper one, right, then what will happen is that if you do it, then there will be some chunks which are not known to the master as having been deleted. Okay. So because of all these things, they have decided that it's best to delete files lazily. Okay. Now they have a similar regular scan of chunk namespace also. The chunk namespace, for example, is kept in the because each chunk is a Linux file, and you keep various mappings between chunk identifiers and the chunk file names of the Linux file names. Okay. So basically, master identifies orphan chunks not reachable for any file and erases its metadata. Okay. So in their design, it turns out a very hard problem called distributed garbage collection is solved slightly simpler in a simpler manner. Basically, because the file to chunk mappings are kept only by the master. Okay. It is in memory actually. Okay. As I mentioned earlier, as we discussed earlier, the chunk master is responsible for all the chunks that is there, and the chunk to file mappings are kept in memory by the master, because once the chunk server comes online, it sends it all the mappings, and then it keeps a consolidated list of all the file to chunk mappings. And any chunk replica is a Linux file in designated directory on each chunk server. Any replica that is not known to the master is garbage, so that can be deleted. Okay. So this way they actually solve a slightly tricky problem in a slightly simpler manner. They also have the issue of stale replica detection. Replica may become stale if chunk server fails and misses mutations. Therefore, they use something called a chunk version number to distinguish between up-to-date and stale replicas. Again, this version number is similar idea what a lot of file systems do. If you reuse an inode number, you have a inode generation number, and that is used to figure out if you are reusing a particular inode block. Okay. So that you don't get into the stale situations. When master grants a new lease on a chunk, you increment chunk version number informs up-to-date replicas. Basically, every time a chunk is being used for write, for example, right? You increment chunk version number and tell all the up-to-date replicas that this is the new version number. Master and these replicas all log new version number before any client notified and write to chunk. If a replica is not available, its chunk number will not increase, version number will not increase. So when is it not available? Because the chunk server is down. So when the chunk server again restarts and reports its set of chunk numbers, associated numbers, it can figure out a stale replica. Okay. It's possible that the chunk server is down or the master itself can be down. Okay. If the master sees a version number greater than its own number for the corresponding chunk, the master assumes that it failed when granting lease, and so it takes higher version to be up to date. Okay. Because it keeps all the information in memory. Okay. So it has lost it and now it can rebuild it from the chunk servers. Okay. Now this particular system has, as we discussed earlier, has designed in fault tolerance and diagnosed systematically. For high availability is one aspect, data integrity is another aspect, and it also certainly supports a lot of diagnostic tools. For high availability, what's important is fast recovery. Okay. So basically, clients and servers, they make requests. If they time out, they again reconnect to a restarted server and retry. Okay. That's a normal operation. It's like the way we use the web. We try something, if it doesn't work, we retry the thing, right? Because if the state is minimal, then this is a very reasonable thing to do. Okay. And the servers are routinely shut down and just by killing the process. Okay. So fast recovery is one, chunk replication is another one. We already discussed this part. We have not discussed this part, the master replication. Basically what we have here is the master keeps also some shadows. These are not mirrors. Mirrors are those in which exact copy is there. These are shadows. What is a shadow? It is got most of the stuff the master has got, but it is slightly delayed. It might be behind by a few operations. So, master's operation log and checkpoints replicated on multiple machines, the shadow machines. The mutation to state committed only after its log record flushed to disk locally and on all master replicas. All the shadows should also get the log, but it's only in the log. It's not the shadow things don't have the actual. Only the log is there, but not the actual data. Okay. So, the important thing, as we discussed earlier, is that one master process remains in charge of all mutations, as well as background activities such as garbage collection and that change the system internally. Okay. Only one master is still there. Okay. When master fails, restart is almost instant, because you detect the failure and you restart a new process, new master process somewhere else, using the replicated operation log. Okay. Essentially, the shadows can also be used as a read-only servers. If for bandwidth purposes, these shadows can also be used for getting certain operations done, but they will be slightly stale. So, the application has to be careful about when it can use these shadows for, because the metadata can be slightly stale. Okay. Other thing that this particular design does is, to avoid the staleness problem with respect to metadata in the shadow servers, it tries to track master by applying log operations. As things are coming in, it tries to do it also. Okay. So, there is also data integrity that is taken care of seriously in the system. It has got 32-bit checksums, it's 32-bit checksums, okay, in memory, and they are logged persistently separate from user data. Okay. Now, it is impractical to detect corruption by comparing replicas across chunk servers. Okay. Actually, chunk server must independently verify integrity of its own copy by maintaining checksum. So, each chunk server should do it. Okay. Reason being, the replicas can definitely become divergent, because it is part of the semantics. Because we notice that with atomic record appends, things can go divergent. Therefore, each chunk server should maintain responsible for its own checksums and checking it. Again, during idle periods, chunk servers scan and verify contents of inactive chunks. We don't have too much time, but basically they also have fairly substantial diagnostic tools with detailed diagnostic logging, mostly done asynchronously to avoid performance bottlenecks. So, with this I want to conclude this today's discussion about GFS. I think basically it is GFS, when it first came out, it probably was the first really large file system, and it had reliability, scalability and availability as core parts of its design. And because it was designed with application in mind, it avoided the POSIX issues, and therefore it could scale with the way it had to be scaled. Okay. So, I think I will conclude here with respect to GFS here. In the next class, I will briefly talk about what is some of the issues of GFS currently as perceived by the designers, and then from there we proceed to other types of large scale storage designs. Thank you.